All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. Today, we are going to switch topics entirely. We've been spending a lot of time now talking about file systems. We've talked about two different file systems. We have talked exFAT to death. It is hopefully burned in your brains, and you can start building something up to read the files out of an exFAT file system. But at this point, we're going to switch over to starting to think about virtual memory. Virtual memory is something that has been kind of alluded to since we've started the course with running processes. But we're going to start taking a look at how an operating system actually helps processes have this idea of virtual memory. And we're going to be starting to think a little bit about the responsibilities of different parts of code and different parts of our system in terms of managing memory for a running process. So by the end of today's lecture, what I am hoping for you to be able to do is begin to explain how a process's entire address space can be provided or supported via the concept of virtual memory. So we're going to take a look at some examples today of confirming partly what an address space looks like from the perspective of a running process. But then we're also going to start to think about, well, what actually is an address space? What actually is an address space? And how much of an address space is actually allocated? Put really simply, we've got these 64-bit processors in everybody's computer. I think it's safe to say everybody's computer at this point has a 64-bit processor. We don't actually use all 64 bits for addressing things. We use about 56 bits, but 56 bits is still like exabytes of memory. It's a huge amount of memory. This machine that I've got in front of me, despite being like a gaming laptop, I've never used for gaming before, and I've never ever used for gaming before. I bought it because I was doing a lot of video editing stuff, and I was doing it previously on a Surface Pro 3, which was awful. It was terrible. It would take like an hour to render a video, and then I got this machine and it's running real fast in about 10 minutes or something. But regardless, this machine does not have exabytes of memory. And I've got a bunch of processes running on here, and all of them seem to think that they have exabytes of memory. So how do we get that? How do we get to that point? I also want to be able to start to describe how the operating system works with the underlying hardware to manage paging. So paging in small type and then virtual memory in big type. We're going to do paging next week. Next week, we're going to keep going with virtual memory, and paging is an approach to do virtual memory. Today and tomorrow, we're mostly just looking at the idea of how do we enable virtual memory to happen at all? How do we enable this to happen at all, rather than trying to optimize it? So in the last little while, we've been spending a lot of time at the bottom of what's called the memory hierarchy. I realize this type is pretty tiny, so I'm going to read some of it out to you. The memory hierarchy, if you've seen the memory hierarchy before, anyone? Some of you have, some of you haven't. Some of you are going like sideways, shake heads. Okay, yeah. Computer memory hierarchy. The memory hierarchy is basically, we've got this triangle shape that describes the size of memory. On one axis, on the base, it describes the speed of memory as we go up, and it kind of inversely describes the cost of memory as we go up. At the very bottom of this thing, we have tape backup. Tape backup, do you all know what audio tapes are? Do you know what audio tapes are? Okay, good. I'm not that old yet. You all know what audio tapes are. Tape backup is kind of the same thing, except it stores digital information, and it stores like many terabytes of digital information. We can get tapes that are like many terabytes, much bigger than a hard drive can be. It's really cheap to buy these tapes per terabyte, but is really slow, like extremely slow. Is fast, like we're talking about many hundreds of megabytes per second, but it's real slow compared to other kinds of storage. On top of that, we've got hard drives. So tape is at the very bottom. Hard drives comes next. And this is spinning platter hard drives. They're faster than tape, but they're still pretty slow. They're fairly cheap per terabyte. And they're pretty big. On top of that, we have flash or USB memory. This is like SSDs. Hard drives and SSDs are starting to get squished together into one thing, but SSDs are still significantly smaller than hard drives. Like hard drives and SSDs, we're looking at SSDs that are maybe 2 or 4 terabytes, and hard drives are capping out at more than 20 terabytes at this point. What's that? There are 8 terabyte SSDs now? Okay, they're still more expensive than hard drives though. They're faster than hard drives. They are cheap enough, but they're kind of in the middle of this hierarchy. RAM is fast. It's affordable, question mark. It's still more expensive than buying hard drives. On top of random access memory, we have processor cache. And when we're looking at processor specs, we'll see things like there's 4 megabytes or 12 megabytes or some number of megabytes of L3 cache or L4 cache. That's very, very fast memory. It's also really, really expensive, which is part of the reason why processors are so expensive. And then at the very top, we've got processor registers. These are the fastest memory that you have in a system, but for the amount of memory that you've got, it's also the most expensive kind of memory. RAID and file systems are topics that live at the bottom of this memory hierarchy. So we're talking about drives, we're maybe talking a little bit about tapes, but it's all stuff that's at the bottom. We don't really talk about file systems in terms of RAM because we don't really use file systems in RAM. The memory hierarchy is this nice triangle-shaped thing, and so I thought it would be nice to also include some other examples of triangle-shaped things in this lecture. So some other examples of triangle-shaped things are Bloom's taxonomy. This is something that I use a lot to guide how I am building out a course and how I'm building out lectures. And in a third-year course, we're kind of in the middle of this, getting closer to the top. So I'm looking for you to be able to do things like apply and analyze. At the very bottom of this, we're talking about first-year courses. So knowledge and comprehension is being able to do things like define terms. This is not a course where I've asked you a lot to define terms, and if I have asked you to define terms, it's in the context of being able to analyze things. Another triangle-shaped thing is the pyramids in Egypt. There's a bunch of them in Egypt. There's also pyramids all over the world in different contexts. There's some in South America and in Mexico. And I'd really love to go see those. I went to Peru one time and I saw Machu Picchu, which was amazing. It was really, really amazing to go see Machu Picchu. There's also that weird pyramid thing on US money that's got an eyeball on it. I'm not really sure what it is, but this was in the Wikipedia article for the Illuminati. There's the Bermuda Triangle, which is famously where ships get lost at sea. And then there's the flag of Nepal, which has 2 triangles instead of just 1. Thanks for coming to the lecture on triangles today. We are now moving up this memory hierarchy. We were at the bottom, we're now moving up to the middle. We're going to start talking about virtual address spaces. I may just start saying address spaces, but I want to be clear that I'm always meaning virtual address spaces here. I always mean virtual address spaces, even if I'm just saying address space. This here is a diagram that you have probably seen before. You've probably seen this diagram before, not just in this textbook, but in other courses. You've probably seen a diagram that looks like this before. I'm thinking in Comp 2280. Yeah, in Comp 2280. That's probably the first place you saw a diagram that looks like this. Quick refresher. At the very top of this address space, we have our program's code. We are writing code, assembly language, C, Java, Python, or whatever, the program's code sits at the top of the address space that we've got, starting at around 0 kilobytes. After the program's code, we've got the heap. The heap is where we're doing dynamic memory allocation, and our heap, just by convention, grows downwards. At the very bottom of our address space, we've got a stack. The stack is where we're putting stack frames. We've kind of learned that even this diagram here in terms of threading with processes is sort of a lie because we might have several stacks throughout our address space. But let's simplify this back down to one single thread, and we'll say that our address space has a stack region and it grows upwards as we're calling functions around in our code. I would like to be able to make some observations about this. I'd like to take some time to make some observations about this. The first way that we're going to make observations about this is by looking at a program that I've written that's called addresses.c. You can find this on the course webpage. You can download this onto your own machine. You can run this on Aviary if you want to follow along with me. But let's take a look at what I've got. I've written a bunch of comments in this addresses.c, and when I post this code up, again, I'll make sure that this commented version gets put up on the course webpage for you. But the actual program hasn't really changed at all. The observations that I want to make are from the perspective of a running program. I've got a program here that does really not very much, but it does get some addresses, and that's really what we're looking for. The very first thing that I've got in this main function on line 10 is a void pointer. I want to get a pointer to something, but I don't really care what the type of thing that I'm pointing at is. I just want to have a pointer, an address. And the thing that I'm asking to point at is the address, ampersand, of the main function. Do you all agree with me that the main function is code? Yes, yes, good. Yes, the main function is code. If I get the address of the main function, I should get an address that's somewhere in the code section, in theory, if this is what memory actually looks like when a program is running, virtual memory. On line 15 here, I'm taking the address of the variable that's called main address. Main address on line 10 here, this is a stack allocated variable. It's a pointer, yes, it's a pointer, but it's a stack allocated variable that contains that pointer. If I take the address of a stack allocated variable, I should get a variable that has an address that's somewhere in the stack because it's a stack allocated variable. I should be getting an address that's somewhere down here at the bottom for something that has been allocated on the stack. To get something in my heap, I'll use malloc. Malloc is my dynamic memory allocation function. If I call malloc and ask for a byte, I'll ask for one single byte, I should get back something in my heap. I should get back something in my heap. After I've got these addresses, I'm printing stuff out. And then what I've got is a couple of assertions. The assertions that I've got here are trying to take that diagram, code's at the top, heap comes after that, stack comes at the bottom, and I'm trying to encode those assumptions about this virtual address space. And if my assumptions about this virtual address space fail, then my program should fail with an assertion error. And then I've got a get char at the bottom because I want to block. I want to be able to see the state of this process when it's running. So let's change to that directory. Let's make this code. There's a couple of other things in here that we'll take a look at a little bit later. Clear this, and I'm going to run it. This is addresses.c. Is that big enough? Are those numbers big enough for you to see at the back? You're okay? Yeah, okay. So I print out my PID, and I print out several addresses, and then I get to this get char statement. My assertions did not fire. These did not break on this, so my assertions must have been true, and we can visually see that. Main is at 0x5590A251A180, somewhere around there. That's where the main function is. The code section is going to be somewhere around that. It will start somewhere around that. That ain't 0. It's not 0, but it's the lowest address that we've got here. The stack is at 7FFFA17F4150, which, well, 77 is significantly higher than 55. 7F, sorry, not even 77. 7F is way, way higher than 55. The stack is somewhere closer to the bottom. And our heap is at 5590A125C32A0, which is higher than our main function. The numbers are the same all the way up to here, and then after that they diverge, but the heap is lower than our main function. That's cool. That's good. That's the kind of order that we were expecting to see from this. We can make observations about this program, but I want to do something more. I'm going to look at a file in the proc file system. On Linux, we have a file system that exposes information about processes that are currently running. The file system here it's like a directory structure. And what we're going to be able to see by taking a look at this file that's called maps, in this processes folder in the proc file system, is that we're going to be able to see what its memory layout is from the perspective of the Linux kernel. So I'm going to pop open a new tab here, and I'm going to say less proc. The process ID for this process is 120393. And I'm going to look at this file that's called maps. I'm going to hit Control-Z on that so that I can get a better idea of what this file looks like. Gosh, this is kind of a mess. It's kind of a mess. So I'm also going to take the time to close this program, and what I want to see is the manual page for procfs, the manual page for the proc file system. I'm going to search for maps. Maps is the name of the file that I'm looking for, and this tells me what the format of the file is. This is a helpful thing to look at if we're trying to decode what all these parts are. The first column of this is the address range in the virtual address space that we have for the process. The next column is permissions, and we've seen permissions on file systems. Okay, there's no file systems for memory, but there are file system-like things for memory. We've got permissions. The permissions here are labeled similarly to what they were for our file systems: read, write, and execute. We've got an offset, which is an offset into the file that is in this path name. So offset in the file, you're reading files a lot now, you're doing lseek a lot now, this is that kind of an offset. The dev, this is a device number. We're going to ignore this column for now. This is a Linux specific thing. We're going to ignore it. Inode here is literally what it says on the box. This is the inode number for this file that we are currently looking at in this address space. So let's take a look at the maps for this program. This is that process, or the addresses program. At the very top, we've got 5590A2519000 up to 8000, which is something in the file, and it's starting at offset 0. we've got from A1000 to B1000. And this is a page that has the execute bit set. That value set that we've got there, let me zoom out of this. That range of values contains this. 1A180 comes after 1A000. Okay, so we've definitely got something that's within the range of that code segment. We can confirm that this is the code segment because we can execute the stuff that's in memory within this range. We have permissions to run code that's in this memory range. We've got some more stuff here that's mapped within this file. So at 2000, at 3000 in the offset of the file. And then here's our heap. Okay, cool, good, there's our heap. The heap that's marked here is within this range, 5590825C3000, which is definitely where our heap is up here, 32A0. It's pretty high compared to the base of the heap, but there's other stuff that's happening in this program. Surprisingly, printf allocates memory in the heap. Printf allocates memory in the heap. So by the time we've gotten to the point of printing the heap is at something, printf has already allocated some stuff in the heap for us, which is interesting. It's interesting. We've got some entries here for user lib x86 64 linux gnu libc.so.6. That ain't our code. That is not my code. We've also got entries down here for user lib x86 64 linux gnu ld linux x86 64.so.2. That is not my code. That's not my code. This is a file that has been mapped into memory in the same way that our program here has. It has one block here that is executable. This one here, similarly, has one that is executable. There's one part of this that's executable. The heap that we've got is read and write. The stack that we've got is read and write, but not executable. We should not be able to execute things that are on the heap. We should not be able to execute things that are on the stack. This right here, when I write printf in my code, that is where printf lives. That's where printf lives. Printf is being loaded into my address space, into my virtual address space when my process is starting. Printf comes from libc. malloc comes from libc. A whole bunch of stuff comes from libc. Everything that we're using in the standard library comes from libc, and it gets loaded into our address space here when our process starts. So printf doesn't live in our program. It's not part of home f bristow c file comp 34302023 summer lectures week 5 lecture 17 code addresses. It's not part of that file. It's part of libc. Every program that gets run is going to have this same file, user lib x86 64 linux gnu libc.so.6. We're going to load that same file into the address space of every process that needs it. I want to take this back a little bit even further. So this is the actual memory layout of our address space that has been told to us by what the Linux kernel is saying. This is all being reported to us by the Linux kernel. I'm going to do, stepping back to like part of assignment 1, part of lab 1. I'd like to read this binary file that is my addresses program. And I'm going to use a program here called readelf. Readelf is a program that can let us display information about ELF files, ELF formatted files. Remember that ELF is this binary format for programs that are running on a system like Linux. I'm going to use readelf to tell me about some of the headers that are in this file, because readelf tells me what the offsets in the file for these different regions are. So I'm going to use readelf, and I'm going to say dash, I think it is E. I just had the manual page open. The one that I want is dash E. I want to see the headers for this thing. I'm going to say readelf dash E addresses. And that's going to, it gives me a lot. It gives me a lot. I'm going to pipe this into less so that I can read it. And what I'm going to start looking for here is, these are the section headers for this file. These are the section headers for this file. And when we're looking at that maps file, let's go back to that for a second. The maps file here says that at offset 1000 in the file that we've got here, we've got something that's executable. This is code that we should be able to execute. When I readelf this file, we've got this kind of like everything's jammed together. It's very hard to read. It's very hard to read. But we've got address, offset. Offset is what it says in the box. This is the offset in this header that's stated in this header about what's going into that part of the file. And header number 12 here is this .init and prog bits. And what I think we could safely assume prog bits to mean is program bits. This is a code section. This is the code section at offset 1000 in the file. That's cool. I can see that you're all super bored, but I think that that's super cool that we can make this connection from, I've got a program that's running, that I can see addresses from its perspective. I can see what the kernel says about the addresses and the ranges, the address space for that program by looking at this maps file. And I can see from the program itself, when it's not even running, where things like the code section are. I can actually see where those things all get tied together. We've seen what this is. We've seen what these different segments are. We've got 3 segments: the code segment, the stack, and the heap. I'm going to ask you this question in the form of a Mentimeter, and we're going to step through it. But I'm going to give you like 20 seconds just to think about this, just to talk about this with the person next to you if you want to. Who has the responsibility of managing the contents of these 3 different segments? Who has the responsibility of managing the contents of these 3 different segments? Take 20 seconds, just think about it. The options that I'm going to give you are the operating system, your code, so stuff that you wrote, a user, somebody that's running your program, or nobody has this responsibility. Take 20 seconds, let me pop up a Mentimeter. So let's start with just the code segment. Who or what manages the code segment, the contents of the code segment? So a process is starting up. We've got to put something in the code segment. Who's responsible for that? I'll give you like 5 more seconds to answer. All right, let's take a look. Okay. this is a good distribution to me. The biggest answer here is the operating system. Second answer is the standard library. And the third is the code that you wrote. I'm going to take a step out of Mentimeter here. And I'm going to go to this website here. I'll put a link to this up on the course webpage after class. This is a website that is called, oh gosh, what is it called? It's like the Source Code Explorer, Elixir, the Source Code Explorer, Elixir Cross-Referencer, Cross-Referencer. I like this website because it will allow us to kind of like click on links for tokens and stuff. So if I have something that's a function name, I can click on the function name and I can start to see what other uses of this function name are, where it's been declared, where it's been defined, where it's used. This is the source code for the Linux kernel. This is part of the source code for the Linux kernel. This Linux kernel source code is like 20 million or 30 million lines of code. It's big. This is one single file in the Linux kernel. This function, as you can all read, is called loadelf binary. It's called loadelf binary. And one thing, oh gosh, one thing that I like about this is to shut GCC up. One thing that I like about this is, yes, this looks like an unreadable, just like barf of acronyms on the screen. Yes, it does look like that. But this is just a C program. It's just a C program. There's nothing here that at this point you wouldn't be able to figure out what this does. It's just a C program. There are directories in the Linux kernel that are architecture specific. So like that whole idea of a dispatcher has to know what registers there are on a processor. There are things that are assembly language for that specific architecture. But a lot of the Linux kernel is just C. It's just C. What I want to look at here is loadelf binary. And the really important parts that I'm looking at here are on line 837. Start code, end code, start data, end data. These are values that are being used in this function, which is pretty long. I'm not going to lie to you. This function is quite long. It's really long. We're not going to step through any of this. We're not stepping through any of this. But this part of the Linux kernel, this is bin format, binary format elf. This is the thing that's responsible for taking that file that's on the file system, reading it, and loading that into a virtual address space. I'll put a link to this up there if you want to take the time to read this on your own time. The important part that I'm trying to get at here is it's just C code, it's just C, it is just C, but also yes, it is our operating system that's responsible for setting up the contents of the code section for a virtual address space for a process. Let's ask the next question here. Who manages the stack segment? Hold on a second. Hold on a second. No, stop. Please stop. Hold on a second. Just hold on a second. There, just in case you answered already, now you can answer again. It was the operating system. That's the one that's managing the contents of the code section. Yeah. I'll give you 5 more seconds to answer. All right, let's take a look. Okay, so I took a moment to stop here and like add this extra option. So why would I add this extra option suddenly in the middle of the lecture? Yeah, okay. I am going to point at these two in the middle here, the compiler and the code that you wrote. The operating system, I'm going to say it's a correct answer in the form of, yes, this has the responsibility of creating the stack segment in the address space, but it does not manage the contents of it. When you call a function in your own code, it's all in your own code. You're not asking the operating system to run this function for you. Your compiler is making like jump to this address instructions in your code. Way back when you were in Comp 2280, I'm pretty sure you had an assignment that was like, write you a stack, build the stack. Did you do that? Yeah, okay. Yeah, build you a stack. When you're writing assembly language code, when you're at that low of a level and you don't have a standard library, it's all you. It's all you doing this. When we're writing C, it's the compiler's job to emit these instructions for us. When I call a function in C, it's the compiler's job to take that call, put all of the right arguments in the right place on the stack, and then jump to that function call. It's the compiler's job to emit those instructions. Managing the contents of the stack is one of these two options, the compiler, code that you wrote. The OS definitely creates this segment, but it doesn't manage the contents of this segment. Your parents using your program. Good, I'm glad somebody picked that. Yeah. Here's the last one. Who manages the contents of the heap section? I'm not going to stop and add the compiler here. Okay, I'll give you 5 more seconds. Yeah, yeah, absolutely. It kind of depends on what language you're writing in. So if you're writing assembly language, it's going to be you writing this code yourself. If you're writing in a language like C, it's your compiler that's compiling down to assembly language. Yeah. When we're declaring variables, that's a fair point. I'm going to go back to my code here. I'm going to take a look at addresses.c here. In addresses.c, I don't have a choice about this being a stack allocated variable. It's just a stack allocated variable. I don't have a choice about this being a stack allocated variable. It's just a stack allocated variable. I don't have a choice about this being a stack allocated variable. That is a stack allocated variable that contains the address into the heap of a place where we can use memory. Yes. This function call allocates memory in the heap that we can use, but this itself is a pointer to that address, and that is a stack allocated variable that contains that address. Does that make sense? Okay, good. Okay, who manages the heap segment? Yes, the OS does, again, create the heap segment. It creates it when it's setting up this whole virtual address space for our process, but it doesn't manage the contents of it. It manages the size of it, but it does not manage the contents of it. Our operating system, once it gives us this heap space, doesn't care. Does not care at all what we put in it. That is something that we are responsible for. The standard library is something that manages the contents of the heap segment in the form of it's allocating and deallocating parts of the heap for us. When we call malloc, We are asking our standard library to allocate some of the heap that has been allocated to us by the operating system. When we call free, we're telling our standard library, I'm done with this memory that you allocated to me. But the OS doesn't know or care about that. Doesn't care. It does not care. The code that I wrote, obviously I'm putting the bits inside of what I get back from malloc. I'm doing that. That's my job. My parents are not doing that, and nobody, well, maybe nobody is doing it if you're just like, I don't know, mallocing everything. Okay, so in this case, our OS, yes, is responsible for creating that segment for us, but beyond that, it doesn't do much. It maybe resizes it, but we're not actually doing anything with it. The standard library is indeed what's going to be managing the allocations to this heap. The code that I wrote is actually putting the bits in here. These are the two answers that I'm looking for. My parents are not doing it. Nobody is doing it, maybe sometimes. Okay, so let's try to run an experiment to confirm that what we've said just a second ago is true. Let's try to run a piece of code that asks for a bunch of memory on the heap just over and over and over again. And the way that I want to run this experiment is to ask what system calls are being made by this program. If the operating system is responsible for managing the contents of the heap segment here, if this is true, then what I would expect is that if I call malloc over and over and over again, I would get lots of system calls that are asking the OS, please allocate memory for me, please allocate memory for me, please allocate memory for me, please allocate memory for me. I want to check that out. I want to try that. So let's go back to my code examples here. The one that we're going to be looking at now is allocate.c. This is a very bad program. This is a real terrible program. This is also up on the course webpage if you want to play along here. This is a program that has a main function. It's got a loop with a hard-coded upper limit of 100,000. And we are allocating in this 1 integer's worth of space on our heap. We're incrementing the contents of that so that our compiler doesn't say, oh, you're never actually using this, and I'm just not going to include that line of code. We are incrementing it so that there are some side effects in that memory. We're printing it out so that our compiler doesn't say, oh, we're never actually using that again, so I'm not going to do that. We're printing it out so the compiler has to include it. And then we're going back to the top of the loop and just doing it all over again. Just constantly cycle. Ask for more, ask for more, ask for more, ask for more. Never stop. Never surrender, never give up. I don't know how the rest of that goes. Let's say allocate. It runs, it prints out a bunch of addresses. It prints out a bunch of addresses. Great, that's good. What I actually want to do, I'm going to say print this out and redirect the output to something that's called dev null. Dev is the devices folder, the file system for devices. Null is basically a garbage can. Just send it to nowhere. I don't want this output. I don't care. Just redirect all output to that. Any calls to write, the write system call to this file are just going to get binned. They're just going to go nowhere. I get no output. Good. That's kind of what I want to see here. I'm going to use strace. I want to know what system calls are being made by this program when it runs. I want to know what system calls are being made. I'm going to expect that there's going to be a bunch of system calls because it's writing stuff in a loop. There's a big loop that writes a bunch of stuff. Let's run this. And we get, yes, a whole bunch of write calls, a whole bunch of write calls. That's a little more than I really want, though. Let's take a look at the manual page for strace. And what I'm looking for is those filters. So the trace equals filters. And the things that I'm looking for in these trace equals filter Memory looks like an ideal candidate. This looks like an ideal candidate for what I want. This is the thing that I'm trying to test, so this is what I should probably filter on. So let's try running strace with that option. So -e trace is equal to, and then it's percent memory. Let's run this again. All right, okay. So in my loop, I called malloc 100,000 times. I called malloc 100,000 times. Let's go back to the code. Let's change this to 100 times. Let's run that again. Okay, so we're changing something. In terms of memory, there's a bunch of this stuff that's happening: mmap, 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 mprotect, 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 munmap, and then brk, and then brk. So something is happening. Something is happening. It's not 100 times. I've called malloc 100 times, and there's 2 of these calls. We'll change this to 1,000. We'll make it again. We'll run it. Okay, it's still just 2. Still just 2. I'm going to run this again. 10,000. We'll make it. Now it's 4 times. It's 4 times. Okay, so I'm hoping what I see here is that even if I'm making this call 10,000 or 100,000 times, the number of calls to this brk system call are not being made quite as often as I am calling malloc. System calls are being made. They are being made. And that implies that we have to ask our OS for something, but we're not just constantly asking our OS, please give me more, please give me more, please give me more. We're asking something. What is this brk system call? Let's do man-brk. Man-brk says, this is a function that changes the data segment size. I'm going to go back to my web browser here, and I'm going to go back to this address space. With this address space, with this virtual address space, we've actually got 2 parts that our program is going to use. There are 3 things here, but there's really 2 parts that we're using. There's the stack segment, and the stack segment starts at about, I don't know, here. If this is the middle, and downwards, we've got the stack segment. If we go here and upwards, that's the data segment, the program code and the heap. As it is right now, if we're looking at this diagram with all this free space, the data segment size goes up to this 2 kilobyte limit. This is where our data segment stops. This brk or sbrk system call is saying, I would like you to make this slightly bigger, please. Please add more space to this segment. The heap has been allocated already when the program starts. The OS does that for us. It is allocating a heap. We can ask it to grow the size of that heap, change the size of this data segment. But the contents of this, when we call malloc 100,000 times, the actual contents of this are being managed by our standard library. They're being managed by glibc in this case. glibc does need to make this system call brk to ask for that to grow when we need more space in the heap, but it doesn't have to do this every single time because the OS is just going to give us a little more than we needed. It doesn't really make sense for glibc to ask for 1 byte of space. Doesn't make sense for it to do that because that whole mode switch, context switch thing is really expensive compared to just getting much more space than you need and then using that space. Okay, so our operating system then is not responsible for managing the content of the heap. It allocates the heap when our program starts. It's responsible for managing the overall size of the heap. Give me a little bit more space for this heap, please. But that's it. That's kind of where this ends. It's the standard library that's responsible for that. All right. The part of the standard library that is responsible for managing the contents of the heap is something that's called the heap allocator. Here are some heap allocators. JEmalloc is the heap allocator that was for a certain amount of time. I don't know if it is or not anymore. Was used by Firefox. It didn't use glibcmalloc, it used this JEmalloc. memalloc is the Microsoft memory allocator, and glibcmalloc is the one that you are actually calling when you call malloc in the code that you've written. What I'd like you to try doing here, these are all links in the course notes that I've put up on the course webpage. I've also just put these links in today's lecture section. I'd like you to pop these open and spend a little bit of time looking for the interface for this. All three of these, in some way, shape, or form, implement the malloc function. They provide an implementation for this. I want you to try and look at these things. Just pick one, try to look at it, and try and find where malloc is implemented. I want you to try and see if you can find where it calls the BRK or SBRK system call. And if you can, try to find anything about how the allocator manages free memory. There's different strategies and policies for managing free memory and free space. We're going to look at that more when we're talking about segmentation with the way that our operating system manages free space. And it's the same policies that this is using for managing free space. So try to find something, but don't worry if you can't find anything. I'm going to give you a few minutes to take a look at these. To be clear, I'm never going to ask you questions about memalloc. I'm never going to ask you questions about JEmalloc. The exercise here is a lot more about trying to read through some source code that does the stuff in practice of what we're talking about in theory here. So take a few minutes, see what you can find. I would strongly recommend against looking at glibcmalloc. I would not make that choice. glibc is really hard to read. It's really bad. I don't like it. memalloc is probably the easiest one to read. And as much as I don't really care for Microsoft, it's because they're paying people to work on this code. They're paying people to work on that code, so it's good code. So please take a look. Give you a few minutes, and then we're going to get back together, and we're going to keep on moving here. Take 3 minutes, and we'll see what you can find. Does mmap do the same thing as BRK? That's a good question. It doesn't. mmap will take a file, and then it will map it into the address space for your process. So when we were looking at this maps file here, so let me open that again. When we were looking at the maps file, I'm going to say less proc self maps. This is showing us the address space layout for less. When this is started, the way that this works is that these files here, this libc.so.6, is memory mapped into this process's address space. And what that means is that when it does things like read from this address, so 7FFB5EA0000, when it reads that address location in memory, it's going to start getting the contents of this file here. So mmap is for doing that. And BRK and SBRK are for changing the size of what has been allocated to you in that data segment. All right. Was anyone able to find a malloc? It's okay if nobody was. And J.E. Malloc? Okay, well, what did you find? Let's take a look. What did you find? In which file? Hook? Yeah. Hook.c, line 19. So what I'm assuming you were looking for was malloc as a keyword, is that right? That's totally fine. That's the strategy that I was expecting you to use for this. However, it is interesting that we found a mutex in here. It is interesting that we found a mutex. Doing memory allocation like this, it kind of has to be locked, because if you have a bunch of different threads trying to allocate memory at the same time, you have to lock the data structures that you're using internally to say which parts of this heap have or have not been allocated. Which parts of the heap have and have not been allocated? There's no file system in memory, but there sure are a lot of file system-like things in memory. We've got this allocation bitmap in exFAT that says which clusters are used and not used, allocated and not allocated. We've got to have data structures in our heap allocator to keep track of which parts of the heap have been allocated and have not been allocated. There sure are a lot of file system-like things in memory here. Okay, that's good though. I'm glad you found this. It also makes me wonder about threading and file systems, but that's a discussion for another day, I think. Anybody else? Anybody else find anything with memalloc or jemalloc? It's okay if you didn't. I'm going to pop over to memalloc here. I like memalloc. I like memalloc. I like all these Microsoft things, and I just don't really care for Microsoft. We're going to take a look at memalloc, and one of the things that I want to do with this, once we've taken a look at it, is I'd like to go through the process of replacing the malloc that's being called with some other implementation of malloc. So when we run our program, we run / whatever, we're getting the glibc allocator. And I'd like to take the time to see how we can replace it. So not use the glibc allocator, but use something else. And that will lead us to, can I write my own allocator? And the answer is yes, you can. You can do it. I believe in you. You can do it. You can write your own allocator. You won't have to write your own allocator, but you could do it. You really could do it. If you don't run into deadlocks. Yeah, I guess so. Yeah. So memalloc here is a fairly well documented and I don't know, managed memory allocator. It's got lots of good documentation about how to build it. It's got lots of good documentation about how to use it. It's got lots of good documentation about how to evaluate its performance compared to other memory allocators. When I'm thinking about trying to find something on a page, on a source code repository like GitHub, I'm going to use this search feature, and I'm going to look for malloc. And what I'm not looking for is issues. I don't really care about issues. I want to look through the source code. So I'm going to click on code here. What? You have to sign into GitHub to do it now? Two-factor verification as well. I'm not going to sign into GitHub. I don't want you to know what my GitHub username is. You follow, yes. It's pretty obvious what my GitHub username is. I still don't want to sign into GitHub right now. So what I'm going to do instead is I'm going to, in this directory that I've got here, code, this is the examples that I've got for today. I'm going to clone this repository. So I'm going to say git clone. I'm going to paste that in. It better not make me log in on the command line because that would be really annoying. OK, so I've cloned this repository. And I'm going to use some tools to try and navigate around this, this repository. So it's called memalloc. And I'm going to try to find, I don't know, the name of a file that has malloc in it to start. That's my first strategy here. So I'm going to use find, and I'm going to say name should be something like malloc, and it should end with .c. So my pattern is anything to start, anything after the word malloc, but it should have .c as the end of the file name. There's nothing. OK, good. There's nothing. The next thing that I want to do is to start looking at the contents of the files. So I'm going to use a tool called grep. Grep is for global regular expression P. I don't know what it stands for. I'm not even sure the people who wrote it know what it stands for. It has something to do with like an ancient Unix text editor. I don't know why it's called grep. It's called grep. Grep-r says search recursively through these files, and I want it to find the string malloc. Any line that matches the string malloc should get printed out here. There's a lot. That's OK. I'm going to pipe this into less so that I can see it. And what we're starting to find here is that in this stats.c, there's a memalloc.h, OK? In static.c, we're including memalloc.h. In alloc POSIX, there's memalloc size, memalloc usable size, good size, memalloc aligned. This is all in that alloc POSIX. We've got similar functions here in alloc override. There's window-specific directories. There's a lot of Windows-specific stuff in here. There's some OS X stuff. OK, this is actually more involved than I thought it was going to be. We've got this page.c, and this is actually starting to look like what I'm interested in. So I'm in page.c here. We've got heap.c. The one that I'm interested in suddenly is this, memalloc generic. This isn't malloc. It's not malloc. It's not just malloc, but it's starting to be something that looks like what we want out of malloc, mainly because it's got a void pointer as a return type. Mainly because it's got a void pointer as a return type. This is close enough for me right now. We found something in here that looks like something that does memory allocation. Here it is as an extern here, memalloc. This is good enough for me. We found something that looks like a memory allocator here. The other thing that we're thinking about is strategies for managing free space. I'm going to try this search feature again and hope that I don't have to log in. And I'm going to search for free space. And I'm going to, I don't want to look at the code because it's going to make me log in. And all we can search through is issues here. Curse you, GitHub. Curse you, GitHub. Let's search for grep -r. And we're going to use the word free. Free here is going to tell us a bunch of free software licenses, which is fine. It's fine. It's going to give us a bunch of free stuff. Let's search for the word space within this. Check if free space is available. All right. Free space, and that's it. Good enough. This is as far as I care to go for today. What we are going to look at a little bit later in the course is free space management policies, and we'll be able to come back to this and start to think about what free space management policy this is using, if it is or is not using a free space management policy. All right. One of the things that this advertises itself as being able to do is replace a library at runtime. It replaces the malloc library, standard library call. We're going to try doing this. This is, you can shut your brains off right now if you don't care to follow along with this. This is not going to be part of the final exam in any way. This is more just like an exercise for you. Slam the pencil down. This is more just like out of interest. How can we do this? Did you have a question before I move on? Yeah, thanks. So I can't use the GitHub search, so I'm going to do grep -r brk. And on os.c, it's got comments about sbrk. In prim.c, we have something about brk, unable to allocate with sbrk, and in this prim.c, this is where it's calling sbrk. That's what changes the size of the data segment. So this is at a point where it needs to ask for more heap space from the OS, but it's not going to call this constantly. It's only going to call this when it internally runs out of free space. Wouldn't that, would it waste a lot of space? Yeah, it might. So it might waste some space by asking for more than it needs, but it's still better to waste the space that's unused than it is to constantly have to ask the OS to make that bit space bigger. Yeah, it's a bit of a trade-off. It's a trade-off. In the context of sizes that we're talking about here, we're talking about kilobytes compared to gigabytes of memory that you have in your system. So it's almost to the point of being irrelevant. So let's take a look at this. Again, yeah, pencils down. You don't actually have to keep along with this if you don't want to. This is more just kind of out of interest's sake. So one of the things that memalloc says that we can do is we can use it to be able to replace our own malloc call, replace the malloc call that's being made using this approach. Memalloc is a drop-in replacement for malloc. We can use it without making any code changes, using this LD preload special variable that will cause a program to change the way that things are being mapped. So let's try build this. The way that we build this, if I remember correctly, I don't remember how to do it. So let's go down to the documentation here and let's check out how to build this thing because it tells us how to do this. I'm going to scroll down a little bit. Usage, building, that's the one that I really want to see. I'm going to make dir -p. Out release. Change to out release, cmake ... make. Cmake, for the record, is a kind of like a different alternative to make, and it gives you a lot nicer, shinier, colored looking output and progress. So we've got this made. What we're looking for is a file now that's called memalloc.so, libmemalloc.so, and I'm going to do that with this. So I'm going to use the find command line tool, libmemalloc.so. It's right there. It's in the directory that I'm currently in. It's right there. It's in the directory that I'm currently in. And then what I want to do is I want to run that program that we were just running, allocate, but I wanted to use libmemalloc.so instead. So let's try that. I'm going to switch to using bash here instead of fish, which is the shell that I'm normally using, because setting the environment variables behaves a little bit differently in different shells, and I want to kind of follow along with what they have there. The way that we're going to set an environment variable for this specific program is we're going to say ld preload is equal to, and this is going to let us pass in the path of the thing that we want it to load into memory. So memalloc out release libmemalloc.so, and then I want to run my allocator. So allocate. That was great. That was really good. That's it. We're done. We've done it. We've replaced malloc with libmemalloc. How do we know that that's actually happened? How do we know that that's actually happened? Let's take a look at a couple of things here. So we've replaced memalloc. We've replaced glibc's malloc with memalloc. Let's try running this with strace. So strace allocate, and we're doing -e trace is equal to memory. And I'm going to do that dev null thing again. Hey, there's no brk system call being made. But my program didn't crash. My program didn't crash. There's no brk system call being made. If I do this, go back to just strace, brk is called a bunch of times by glibc, but memalloc is able to run and not call brk at all. Well, so let's try something here, allocate.c. Let's add getchar. Let's block. Let's see what this is mapped as when it's running with memalloc. So we're blocked right now. We're stuck. Let's try taking a look at this program. Its process ID is 125616. So less proc 125616 maps. Okay, so we've got this libc still mapped into memory at this range 7FEE27600. And then we've got memalloc mapped in at 7FFE2795000. And then we have it mapped in at 7FEE2795600. Okay, so when we loaded this in with this LD preload thing, we've basically said, yeah, okay, you should still load the standard library because we have a bunch of functions that we need to be able to call in that. But let's also load this library in the same address space. Let's load this library in the same address space and start replacing some of those functions that we've got. Sigwinch. Okay, so yeah, yes. Okay, good. Now we can turn our brains back on for a second. That's the end of, like, we don't have to do this on the final exam. This does kind of lead us to the state of, well, maybe I can actually write my own allocator. I've got this program here that's called mymalloc. And mymalloc makes a heap. This is not a thread-safe allocator, by the way. This is not a thread-safe allocator. It makes a heap, and it does that by creating a giant array. It has a current pointer. This is where we currently are. It does not replace free, so you can't actually free any memory that you've allocated here. And eventually, it's just going to bail out because we're going to segfault, because we're going to allocate too much memory, and there will be nothing left. But what I've got here is, right, when you're called print to standard output, hello from mymalloc. Let's do the same thing that we just did with memalloc, but let's do it with mymalloc.so. So I'm going to say bash ld preload equals mymalloc.so, and I'm going to run allocate. And it's blocked, and it works. It works. I actually can't believe that that worked. I think I just changed the heap size here to be just small enough. Let's go back. I'm going to do this really quick. Let's do allocate.c, and I'm going to change this now to be significantly bigger than the heap that I've allocated here. So I'm going to say 10 million. I'm going to allocate 10 million bytes. I'm going to make that, and I'm going to run it again. And it's not working. It's not doing what I want. Okay, good. This is an excellent time to end class while I'm embarrassed about trying to do a demonstration. Okay, so what I want to do is pop over here. I'm going to say this. Memory's got a certain layout from the perspective of a process. This is what our virtual address space is. We've got that code segment, we've got a heap, we've got a stack. The operating system enables this layout. It is creating all of these different parts of this address space for us, but the responsibility of the operating system kind of ends there. It kind of ends at, here's the layout, let's put some code in. Now we're sort of done. We'll maybe change the size of that segment, but we're not actually responsible for managing the content of what's going on in there. The operating system may manage less than we originally thought, but maybe it just manages something that's slightly different than we had originally thought. We'll talk about hardware translating addresses tomorrow. Thanks all for your extra time, and I will see you all tomorrow. Bye, everybody.